crystal defects we are going to discuss in solid materials. We have talked about different possible crystal systems in which individual atom or ions can be arranged to give us a three-dimensional structure. But remember that there may be a certain imperfections. As we know, nothing is perfect. So same applies to our crystals too. There may be a certain possible defects in the crystal structure that having certain implications or that may lead to certain properties into materials. Now let's discuss first briefly about these crystal defects. We know ideal crystal having a regular arrangement of units throughout solid in 3D structure, but defects in crystal mean there are certain ambiguities, certain irregularities in the arrangement of constituent particles. So briefly we can classify defects into two categories. There are two types of defects: point defects and line defects. Line defects that are present throughout a linear structure. Point mean at one particular lattice point in three-dimensional crystal. Now we start first with point defects. Point defects are irregularities or deviations from ideal arrangement around a point or atom in a crystalline substance, like you see here. Here we see a regular arrangement of, you can see, velvet green. On certain point you saw there are defects. Velvet line is absent, in spite this white dot is present. Similarly here in green ball place we having a white ball here. So these are the breaking of regular structure. Such point, because it's present only at one particular point, so these are known as point defect. Point defects can be classified further into three types. Now if you remember, we started with defects. They can be line defects, point defects. Now we are talking about point defects that can further be classified into three types. Stoichiometric defect first type. Stoichiometric point defects do not disturb the stoichiometry of the solid. That is, these are also called intrinsic or thermodynamic defects. So in the stoichiometric defects, the stoichiometry of a compound is not disturbed. It remains the same as in ideal crystal. There are four basic types of stoichiometric defects applicable to ionic as well as non-ionic solids. Let's discuss. We are going to talk about now stoichiometric defects. Very first defect is vacancy defect. What it is? A crystal in which some of the latest sites are vacant is said to have vacancy defect. You see, we having a crystal structure, yellow, red, it's marked by it, and in it red is missing here and one yellow is missing here. So these are called vacancy defects. There is a decrease in density of a solid substance because we know when certain ions or certain atom or molecules are missing, it leads to reduction in density. These defects usually develop when we heat it. So vacancy defect is nothing but missing of certain constituent atoms or group from its lattice. Interstitial defect. In interstitial defect, some of the constituent particle atoms or molecules occupy an interstitial space in its crystal arrangements in 3D Bravais lattice. We having a regular arrangement of the larger and smaller atoms or molecules. But what we saw, certain atoms or molecules will leave their regular position and comes to interstitial lattice, which is a space between the different layers as we discussed earlier. Such defects are known as interstitial defect. These defects increases the density of a substance because we saw in interstitial defects, some of the constituent particles, atom or molecules occupy the interstitial space as we can see here. This is a regular arrangement, but some constituent particles occupy these interstitial spaces. This defect increases the density of solid substance. Vacancy and interstitial defects we discussed so far are shown by non-ionic solids. So these defects are all about non-ionic solids. Another two types of defects, they are about stoichiometric ionic solids. First, Frenkel defect. What is a Frenkel defect? Frenkel defect is shown by ionic solids with smaller cations dislocated from its normal sites to interstitial sites, same like these interstitial defects, but these are shown by non-ionic. This is Frenkel defect is shown by ionic compounds. And here is smaller size cations dislocated to interstitial space. It's also known as a dislocation defect because the cations will still remain in the lattice in the void, so density will remain the same. These defects are shown by the ionic compounds having a significantly smaller cation compared to anion. So zinc sulfide, silver chloride, silver iodide, because of the small size of their cations, they show Frenkel defect. Schottky defect. Schottky defect is a vacant defect in ionic solids where equal cations and anions are missing from its crystal lattice. To maintain neutrality, cations and anions in Schottky defect are of nearly same size. There is not much difference in their cations and anion size. Sodium chloride, potassium chloride, sodium brom, or cesium chloride and silver bromide are examples. Because in Schottky defect we have a loss of both cations and anions from their lattice positions. So such defect reduces the density. Here is the defect. Defect of cation, defect of anion, defect for anion, defect for cation. So equal number of cations and anions are missing in Schottky defect. These are defects in stoichiometric compounds, and the defects will maintain the stoichiometry. Next point defect is, we have discussed only about stoichiometric defect. Next is defects introduced by the addition of impurities in solid crystals. When we introduce a foreign material or foreign atoms in a crystal, some of the atoms are replaced to maintain electrical neutrality. Some atoms create empty space lattice positions. That is in case of the charge is imbalanced by the addition of impurity. Third defect is non-stoichiometric defects. Inorganic solids which contain the constituent elements in non-stoichiometric ratio due to defects in the crystal structure are known as non-stoichiometric defects. Now, let's discuss about non-stoichiometric defect first.